Morning to one and all. My name is Sohit and roll number 4J8 and I'm from E section. Today my topic is about high-speed complex number multiplier and inner product processor. Abstract. Complex number arithmetic computations are one of the key arithmetic components in modern digital communication and optical systems. Complex number multiplication and complex number inner product play a unique role in these applications, which our topic is about. In this paper, a complex number multiplier and complex number inner product processor based on a redundant binary representation are represented, which will be represented as RP throughout the presentation. This work is an extension of a previous real fixed point inner product hardware design with the proposed algorithms. The complex number multiplication is reduced to parallel array multiplications, and the complex number inner product is produced using a RE addition tree. This proposed inner product processor can be reconfigured or controlled to perform different computations such as inner product processing or parallel multiples for real and or complex numbers. The design results not only in simplified arithmetic operations, but also in a highly parallel and simple architecture when compared with other methods. Simply the abstract of our topic says that the inner product processor can be reconfigured or redesigned uh, for controlling to perform different computations such as inner product processing or parallel multipliers for both real and complex numbers. We will be discussing about this throughout the topic, throughout our presentation. And coming to the introduction, complex number arithmetic computation is a key arithmetic feature in modern digital communication and optical systems. Many algorithms based on convolutions, correlations, and complex filters require complex number multiplication, complex number division, and high-speed inner products. Among these computations, complex number multipliers and complex number inner products are becoming more and more demanded in modern digital communication, modern optical systems, and radar systems. Multiplication is an essential operation for high-speed hardware. Implementation of complex number computations. To compute the product of two complex numbers, the conventional method is to use four binary multiplications, one addition and one subtraction. Suppose define two complex numbers as A is equal to AR plus JA1 and B is equal to BR plus JB1, where AR is the real component of the complex number and A1 is the imaginary part. Similarly for B, BR is the real component and B1 is the imaginary component, where the next point says that where AI, AR, BR and BI are the real and imaginary parts of the complex numbers A and B. Since the real part and the imaginary part combined gives you the complex number, multiplication of A and B is given as A into B is equal to AR into BR minus AI into BI plus J into AR B1 plus A1 BR. The first point of this slide also says that the conventional computations method is used for four binary multiplications and one addition and one subtraction. Yet the subtraction is done by A1 B1 and one addition is done by the imaginary part of the whole multiplication, that is AR into B1 plus A1 into BR. And the four multiplications are between the two real components and imaginary components, and between the imaginary and real components, that is AR B1 plus A1 BR. To reduce the arithmetic complexity of the complex number multiplication and algebraic transform given in the equation 3, that is the previous equation proposed by the Balhet. So this is the that is A into B is the multiplication proposed by Balhet. It is very complex, and this method saves one real number multiplication at the expense of two more additions and more than one subtraction. So we have come up with a solution called RB complex number multiplier. That is the redundant binary complex number multiplier. This redundant binary representation is one of the single digit number representations originally introduced by Avicenna's 141 for achieving any propagation free addition. RB numbers differ from the conventional two's complement representation in that the individual digits comprising a number may have negative values as well as positive values. The process for this RB complex number multiplier is first we have to conversion of two's complement to RB and then apply the RB complex number multiplier. So these are the two methods for the RB complex number multiplier. Those are conversion of two's complement to the RB. That is, in the conventional multiplying, we use the conversion of two's complement, and that we have to convert into RB, that is redundant binary system. And then we have to apply the complex number multiplier. Now, what is conversion of two's complement to RB? How do we do it? Let's see that the binary sign digits can be coded in several ways. In this work, the binary sign digits -1, 0, 1 are coded as 0, 0, 0, 1, 1, 0, 1, 1, respectively. Here we look at the addition of two's complement binary numbers. In the RB architecture implemented here, an RB number A can be derived from the addition of a pair of two's complement number A and B, where n is the bit length. Now, about RB complex number multiplier, Shin and Jian proposed a high-speed redundant binary implementation of A0 B0 plus A1 B1 and A0 B0 minus A1 B1 for a complex number multiplier by combining or you can say mapping equivalent two's complement partial products across A0 B0 and A1 B1 multiplications to generate the redundant binary partial products. This method is illustrated in figure 1 for the imaginary part A0 B0 plus A1 B1. Slightly different circuits are required to handle the real and imaginary parts. Note that the number of partial products being summed is 50% compared to a normal two's complement multiplier. So this is the cross partial product structure of A0 B0 plus A1 B1. You can see that the binary number partial product generated for A0 B0 and A1 B1 are mentioned separately in the head of this flow chart, and these are converted to two's the complement of two's is converted to RB, and they are mapped separately for A0 B0 and A1 B1, and they are both are mapped again to the one RB sum of A0 B0 plus A1 B1, that is RBA, which is mentioned in the bottom of the flow chart, that is summed to 50%. And this is the RB inner product processor for real and complex numbers. That is both, you can see that A0 B0 plus A1 B1, A2. So we can multiply for so many numbers. This is for real and complex numbers. So we can conclude that a new high-speed complex number multiplier using redundant binary number representation is presented in this presentation. Based on this proposed method, a reconfigurable or controllable inner product processor that can be used for both real and complex number computations is investigated. With appropriate control or reconfiguration, the inner product processor delivers high performance for computations such as parallel multiplication and inner product processing for both real and complex numbers. The proposed scheme provides not only simplified arithmetic operations, but also a highly parallel and simple architecture when compared with the other methods. Thank you.